And this is G485 homework booklet question 6. So part A straightforwardly is asking us to define capacitance, simply the charge per unit PD, or you can give that as charge divided by the potential difference. Move on to part B then. We've got two capacitants, 150 microfarads and 450 microfarads connected in series, and we've got a battery with EMF 6 volts with negligible internal resistance. That point about the negligible internal resistance just means that you can assume that the total PD across the components is the same as the EMF. There's no lost volts in this case. So what are we going to be asked to do? We're asked to calculate the potential difference across the 150 microfarad capacitor, calculate the charge stored in that 150 microfarad capacitor, and to calculate the total capacitance of the circuit. Now, I'm going to take you through this in two ways, one of which kind of answers the questions in the order that they're asked, but has a very, very difficult starting point, and the others are dependent on that. We'll then have a look at an alternative, which is, oddly enough, to start at the end and work forward. So, we're asked to calculate the potential difference across the 150 microfarad capacitor. Now, we've got the two capacitors in series. What that means is that the total charge on the capacitors overall must be the same as the charge on each capacitor. So we've got electrons flowing onto that bottom plate, off the top plate, onto that bottom plate, off the top plate, and it's the same amount of charge each time because everything's in series. So if each capacitor has got the same charge, basic equation Q equals CV, so I've got a constant capacitance times PD, so CV for that capacitor must be equal to CV for that capacitor because the charge on that capacitor is the charge on that capacitor, so CV is constant. Now, because just looking at the numbers, 150 is a third of 450, then the PD on that must be 3 times the PD on the 450. So the 150's must have a PD that's 3 times bigger. We also know that they've got to add up, those PDs have got to add up to 6 volts. So I'm looking for a PD that is 3 times bigger than that one. And they've got to add up to there. So that if this has got to have 3 times the PD of that one, that's got to have 3/4 of the PD, that's got to have 1/4 of the PD. They've got to add up to the 6 volts, so that's got to have 3/4 of the 6 volts, 4.5 volts. You might want to just rewind that and listen to that logic, because it's not straightforward, but we do get 4.5 volts on the 150 microfarad capacitor. Moving on then, now we've got that potential difference on that 150, everything else becomes fairly straightforward. We've got the charge on the 150 microfarads, so I'm just doing CV, I've got 150 times the V, I end up with that value, 6.75 times 10 to the minus 4, and then I'm asked to calculate the total capacitance of the circuit. Now, following this logic, there is another way, which no doubt you spotted, but following the logic of that we've been following so far, if I've got that charge, then I know that charge, as well as being the charge on the 150 microfarads, has to be the charge on the overall capacitance, so that the total charge is that, and the total charge is for total capacitance times the total PD. Quick rearrange so that I've got the total capacitance is the total charge, which has to be the same as the charge on the 650, divided by the total PD. So I've got the 6.75 times 10 to the minus 4 divided by that 6 volts total PD. I end up at 1.125 times 10 to the minus 4 farads, 125 microfarads. Okay, so I said that was one way of doing it, but there is, importantly, another way of doing this. So I could start off alternatively simply by working out the total capacitance using the standard capacitors in series formula, that the total capacitance, 1 over the total capacitance, is 1 over 150 plus 1 over 450, both times 10 to the minus 6, gives me that 1.125, that should be times 10 to the minus 4 there, farads, 125 times 10 to the minus 6. So that would be one possibility. And of course, even if I'd done parts 1 and 2 the way I've just explained, I could still have done part 3 that way. What's interesting though is if I'd done that way, that would then allow me to work out the charge stored on the 150 microfarad capacitor by saying it was equal to the same charge that I've got on the overall capacitor. Now I've got the overall capacitance, I can just multiply that up by 6 for the overall PD to get the charge on the overall capacitance, and that will be the same as the charge on each one. And then I could go the final step and say, going backwards, saying that if I've got the charge on that on part 2, charge on the individual capacitor, then I can work out the PD across it just using Q equals CV for the 150 microfarad capacitor. So I've got the charge, I've got the capacitance, simply dividing the 6.75 times 10 to the minus 4 by the 150 times 10 to the minus 6 and end up the PD. So you've got the option, you can either run forward using this slightly difficult logic about the PD over the 150 having to be 4.5 volts, or you could actually start with part 3, calculate the capacitance. That allows you to calculate the charge overall, which is the same as the charge on the individual one, which then allows you to do part 1, just doing a simple Q equals CV on that capacitor. So one way or the other, you can work your way through that. We're now getting into a charging and discharging. So we've got the fully charged capacitors are disconnected from the battery, and the capacitor then connected with the resistor, and open switch. The PD across the capacitors is measured with a voltmeter of infinite resistance, so there's no discharge happening through the voltmeter. The switch is closed at time t, and measurements of V are made at regular time intervals. Show the time interval for the circuit is about that, so that's a straightforward using time constant is just CR, capacitance, times the resistance, and we get to there. No problem at all with that. And then we're asked to sketch the variation of the PD with time. Now, we know we start at 6 volts, so that's no problem. The point is, over each time constant, over each 5.06 seconds, we drop to 1/8 of the previous value. So I quickly in my calculator did 6 times e to the minus 1, I got 2.2, and the mark there is for having it at 5 seconds somewhere between 2 and 2.5 volts, and the other mark is for having the shape, which I have to say I've drawn pretty awfully on there. That should be smoother. Since I had these values here, it seemed to make sense just to quickly work out the other values and get those some sort of sketch plot to help me get that shape as well. We're then asked to calculate the ratio of the energy stored in the 150 microfarad capacitor to the energy stored in the 450 at time equals 0. Now it works out that it's by far the easiest thing to do to use Q squared, a half Q squared upon C on this event, because if I'm doing a half Q squared upon C divided by half Q squared upon C, obviously my halves cancel, and the point is again that each capacitor's got the same charge, so those cancel off, so I end up with 1 over 150 divided by 1 over 450. That is 450 over 150. It's a ratio of 3. Your alternative here would simply to use a half CV squared or a half QV for each of the two capacitors. You'd end up at the same point but have to have done more sums along the way. And then finally we're asked to state and explain how that ratio varies with time. Now if you've done it by the half Q squared upon C method, it's very, very obvious that it's simply the ratio was just the capacitance over the capacitance. The time equals 0 didn't come into it, what the voltage was didn't come into it, what the charge was didn't come into it. So because they've got the same charge, that ratio remains constant. and so that's the answer to the end. So that, and I think that's my record long video so far, is G485 Homework Booklet question 6.